today. The main focus of today is going to be, and tomorrow night, is going to be to go over and review the most missed, not really the most missed, I should say the most popular questions that pop up on the Regents exam. So questions that pop up consistently year to year to year. At the very least, similar types of questions to the ones that pop up year to year to year. We will start with the June 2014 Regents, which is the second set of questions in that big packet that I gave out in class last week or 2 weeks ago, whenever that was. We might also, as we're going through tonight and flipping through, start looking at more questions in the green books, just because those have the 2015 through 2018 Regents, just to show you how either similar or almost the same these questions are. So again, as you're tuning in, main focus is popular questions that consistently pop up each year. My previous videos on the 2018 Regents and the 2013 Regents will help you look over those kind of niche, weird questions that may pop up. The Part C can be kind of unpredictable. When I say the Part C, I mean those last like 10 or so short answer. They'll take concepts that are relatively easy in the classroom, but just ask about it in very strange ways. And I think we saw a little bit of that with the 2013 Regents exam with that table of the elements. But again, focus of today, or I should say tonight right now, is the most popular questions that pop up every single year. And we'll get started in a sec. I do think people might want to tune into this one because it's arguably the most important one, but I'll get started in a minute. And I'm just going to send out another quick remind just saying what we're doing because maybe that'll get more people to tune in. But as usual, it'll be posted on my YouTube channel, so no rush. Let me just do this real quick. Goal for tonight: review the most popular / repetitive. Repetitive questions on the chemistry Regents. Because I figured at this point, we're kind of at the stage, the Regents is under 48 hours away, that we just need to hit what's important. We can't really go over those really specific kind of questions unless you have questions, in which case, always feel free to ask. Always feel free. You can text me on Remind. I got Remind open on my phone. So, just sent out that message. I'm going to wait a few minutes to let people join in. A few people already texted me on Remind, asked me to wait a few minutes, so I will wait a few. I'm not going to wait too long because, like I said, everything gets posted on my YouTube channel. So, what I will do is do maybe a quick little recap of the 2013 Regents, even start there. So my previous two videos went over this entire Regents. I'm going to just start looking at ones that I know pop up often. So when I start the 2014 one, right after this, you might already see, oh, yeah, that was already on the 2013 Regents. How repetitive does this get? Starting with question 1, orbitals. They like that question. We'll see if that pops up. You're always going to get a bunch of atomic structure-like questions. I can't predict how they'll ask it or which ways that they will ask it, but something about protons, neutrons, and electrons will pop up. Question 3, how light / color is produced by atoms. They always like to throw that in there. Question 10, something about the strong attraction for electrons. That definition is electronegativity. They like to throw that in there year to year to year. Question 8, similar chemical properties. They like to throw that in. So you see like a question like 7, something about atomic structure. Always within the first 10, there is a bunch. 6 was a little weird. A little too easy. Ideal gas. Something about ideal gases will be on there. High temperature, low pressure. Going through these theories, like what's right about it, what's wrong about it. That always pops up. Again, people starting to tune in now. I already went over this Regents exam. I'm just getting us a little prime for what I'm doing tonight. Just looking over this Regents, picking out questions I know are really popular, and seeing if they pop up on the year after. We are doing the big packet that I gave you guys last week or 2 weeks ago. We're gonna start with the second set of questions, which is starting over again with number 1, which is the June 2014 Regents exam. So if you don't have the packet, you can always just follow along. Or, sorry, not follow along. Find it online. All the chemistry Regents, every single chemistry Regents through the decades are available online with answer keys. Entropy, popular. Collisions, popular. You know, questions like 18 and 21, something about like physical properties, separating mixtures, they always throw that in there. Acid-base theory, who's the proton donor, who's the proton acceptor? Electrolytes, love electrolytes. They love it. Always pops up. Excited state versus ground state. Almost always. Again, 32. More atomic structure-like questions. They are popular. People that are joining in, I'm just recapping the previous video. Just looking over popular questions that are on the Regents exam, because a few people said I'll be on in like a few minutes just to wait a few minutes, and I will grant that. So I'm just getting us a little prime for what we're doing tonight. We are looking at popular / repetitive questions from the chemistry Regents exams. This is the June 2013 Regents exam, which I went over today and yesterday. They are both on my YouTube channel. So the next Regents will be the 2014 exam. We're going to look at what are these popular questions and how they are similar year to year to year. You know, particle diagrams are hit or miss. You won't always see those. Saturated versus unsaturated, popular. Something about shifting. Something about shifting. I don't know what, but something. Using table M. Pops up a lot. MAVA equals MBVB. Pops up a lot. General recognition of nuclear equations, predicting the products, using half-lives, stuff like that. Popular. 44, these like pH changing questions, how the hydrogen / hydronium concentration corresponds with the pH change. Popular. And again, they're popular in a way that I can't predict whether they'll be on the short answer or not. They might be multiple choice. They might be short answer. Either way, they will be there. 51, balancing an equation. Almost every year they ask you to balance an equation. Identifying types of bonds. Popular question. BARF. Drawing something. You'll probably have to draw something. What that is, that's not very predictable. So I may or may not go over that tonight. But you'll have to draw something on Tuesday. Heating or cooling curve. One of those will be there. Which one? We'll find out on Tuesday. There's that ideal gas again. They will ask you about ideal gases. I guarantee it. P1, V1, T1 questions are usually pretty popular. Empirical formula is something I've actually noticed pops up a lot. I'm going to crack open a window. Give me one sec. So, empirical formula, they like to ask about intermolecular forces. They like to ask about, watch for that. I'll get started in a few minutes. I don't mind waiting. This is an example of a question that's just kind of weird. Unpredictable aspects of the chemistry Regents. You'll get some weird ones. Using table J. They like you to use table J. You'll notice in like the 3 Regents or the couple Regents that, well, let's say we've gone through a lot of Regents in class. I've reviewed 2 Regents exams on my live streams. You'll notice that they don't have you use table H that much. I don't know why, but it's not a popular reference table. Determining the change in oxidation number, they like that. Increasing the rates of reactions, they like that. Something with these potential energy diagrams will pop up in some way, shape, or form. What they do like to ask about consistently is catalysts. You know, organic, as you've noticed, is one of the more popular, probably top 3 most tested units on the Regents. We got atomic structure, organic, acids and bases, 3 big units on the Regents. Feel free to do those CASA learnings on those topics so that you will be prepared. These like polarity kind of questions, polarity in general tends to be really popular. So we're primed a little bit. We've already gotten a kind of a sneak peek at questions they like to ask about. Let's start to see how many are already going to repeat on the June 2014 Regents. So, people just tuning in, goal for tonight, we're going to look through the June 2014 Regents. Where can you find that? You can find every chemistry Regents from the past 2 to 3 decades. You can find the chemistry Regents that I took online. It's an easy Google search with answer keys. So you can like just print out seemingly infinite amount of chem Regents. But the June 2014 Regents was the second Regents exam in this packet that I gave out to my students a couple of weeks ago. If you don't have it, you can always look up the June 2014 Regents online, or you can just follow along. We might take a peek at some Regents in the review books to just look at the ones that repeat often. So, if you have these handy, feel free to have these out. And let's get started. All right, so let's start looking at questions that are very repeated. Would you look at that? Question 3. Already, orbital. It was the first question on the June 2013 Regents. It was the third question on the June 2014 Regents. They love to ask about orbitals. What is an orbital? First, orbitals deal with electrons and electrons only. So if you see anything about protons, you can say that that is incorrect. The definition of an orbital, this is on my Quizlet that I linked out to you guys, and that is on my teacher site, is the region of the most probable location of an electron. Not the circular path. That is an orbit. That is an outdated model. That's the Bohr model. The most updated model is the wave mechanical model. Point being, they love to ask about orbitals. Excited versus ground state. When you have an electron move from an excited to the ground state, energy is going to get released. So, boop, boop. Remember, excited is the state that's going to be really energetic. It's that state where it's like you jump up on your chair and you're like, woo! That's the excited state. When you get back to the ground, you're releasing all that energy that you just had. You're calming back down. And when electrons do that, they're moving to a lower energy state. And if we're just going to take it one extra step here, they're going to release light of some variety. Release some form of light. So just to make sure we're good there, because they like to ask that part of the question too, might even pop up on this Regents. I don't know. I'm going through this cold. All we've done so far is looked up the June 2013 Regents, kind of primed ourselves with the questions that they like to ask. And now we're already on the June 2014 Regents, and it took us until question 3 to get almost the same exact question they asked the year before. All right, other popular ones. Okay, I would say 8 is very popular. Different things are different. So they often, almost always ask about diamond and graphite. They're like obsessed with it, and they just love diamond and graphite. I think it's just because you're familiar with diamond and graphite. I don't know. That's just a guess. So different things are different. Yes, they are both carbon, but they have different physical properties because they have different structures. You can actually figure this out from process of elimination. Since they're both carbon, can't be atomic numbers. The atomic number of carbon is 6. You can get that from the periodic table. No different. Can't be either of these as well because, again, they are both the same form of carbon. They're just carbon. They're not, one's not carbon 12 and the other carbon 13. They're just good old-fashioned carbon. But we should know that a diamond is a diamond and a graphite's in your pencil, and they're kind of different in their uses and they're kind of different in their structures. So they love to ask this question. Again, goal for tonight is just popular repetitive questions. Here we go. I pointed out the June 2013 Regents. They like to ask this vocabulary term. Strongest attraction for an electron. They love it. Pops up almost every year. What that's basically saying is which one of these has the highest electronegativity, which you can find on table S. So we're going to look up chlorine. We're going to look up fluorine. We're going to look up nitrogen. We're going to look up oxygen on table S. And the one with the highest electronegativity will be the one that has the strongest attraction for electrons. So, electronegativity is right there. We got oxygen at 3.4, fluorine at 4.0, nitrogen at 3.0, and chlorine at 3.2. So, strongest attraction for electrons, highest electronegativity. Who's got the highest electronegativity? Fluorine does. Fluorine has the highest electronegativity of any element on the entire periodic table. You see strongest attraction for an electron and fluorine's an option, you're putting it. But, like I said, most repetitive questions, we've already run into 3 or 4 by question 12. Easy peasy. 13. Well, different things, they're just different. They like to test this idea. And this one's kind of easy because it's pretty obvious that they're different. One is nitrous dioxide and the other is dinitrogen oxide. Clearly those are different things. Sometimes they'll trip you up and have you compare O2 and O3, or they'll do the classic example that we just did like 5 questions ago, diamond and graphite. I don't care that they're both composed of nitrogen and oxygen. The fact that one of them has 2 nitrogens and the other one has 2 oxygens makes them completely different things with totally different properties. The only thing that you can say has similar properties is the same substance. All you did was change it physically. So, yeah, diamond and graphite are both carbon, but they have completely different properties. They don't even look remotely similar. But like solid versus liquid water, they have things in common chemically because they're both just water. They're just in different phases. Diamond and graphite are totally different things, even though they're both made of carbon. Boom. Question 14. Already got to something I told you was going to pop up. Molecular polarity. So, when you deal with molecule polarity, that's when you snap it. All right, there's two different types of polarity questions they're going to ask you. They're going to ask you about molecule polarity, and they're going to ask you about bond polarity. They're two different things. Let's finish this question, and then I'll go over bond polarity. Molecular polarity is when you snap it. So, symmetry, nonpolar. Asymmetry, polar. So if the molecule is symmetrical, it is not polar. If the molecule is asymmetrical, it's polar. Now, I highly recommend that you draw out CH4 before you take a stab at it. CH4, we got a carbon with 4 hydrogens. I'm not going to draw the hydrogens in for all of them. I'm going to make a reminder. Hydrogen is happy with a single bond. You don't need to put any dots ever on a hydrogen. That carbon forms its 4 bonds. The 4 bonds are all the same type of bond. They're all CH bonds. I look at it. It looks symmetrical to me. As long as you don't see those bonds start to bend. When you see bonds bending, like an H2O or NH3, that would make it not symmetrical because they have lone pairs. So if I were to draw water, some of you might draw it like this, and you would get credit for it. Technically, water's bent. You want to draw it like this. But you would get credit if you draw it like this. You might think that's symmetrical because it looks like in math, you're like, just draw the line down, draw the line across. It looks like it's symmetrical. But the fact that we have a lone pair here and a bond here means it's not symmetrical. Because we're not talking about symmetrical in terms of its shape. We want to talk about symmetrical in terms of its charge distribution. And those electrons that are lone pairs are going to have a bit more attraction to the oxygen because they're lone pairs. There's nothing else trying to take them away. Versus the hydrogens fighting for the electrons that oxygen's sharing with it. So we have a little asymmetry going on here. So water, you would say, is polar because it's not symmetrical. It's asymmetrical. Methane, CH4, you would say is not polar because it is symmetrical. So snap it and then match the answers that match snap. So at the very least, before you even draw it, snap it. Symmetry is nonpolar. Oh, this one says symmetry. This one says nonpolar is asymmetrical. That doesn't make sense. Asymmetrical is polar. Well, the answer choice above it says polar is symmetrical. That doesn't make sense. Then apply it to the drawing. Give yourself the best chance to get the answer right. Earn your points. No silly mistakes. We said CH4 when we drew it looked pretty symmetrical to me because all the bonds were the same. They were all CH bonds. Therefore, it is symmetrical, which makes it not polar. I did mention we were going to talk about polar bonds before I forgot. A polar bond is defined as having 2 atoms with different electronegativities bonded together. So a CH bond is polar because carbon and hydrogen have different electronegativities. Really, the easiest way to do it, because I've almost never ever seen an example where they give you a carbon-sulfur bond or some 2 different atoms that happen to have the same electronegativity. Usually, if it's 2 different atoms, it's polar bond. If it's the same atoms, 2 H's, 2 O's, those are all nonpolar bonds because their electronegativities are the same. Double check table S if you're not sure. It usually, like I said, 2 different atoms means that you have a polar bond. But again, check table S. You can look it up. You have so much time to take this Regents. You're going to go into this as the last Regents you took was your math Regents, where so many of you were like, oh my God, that took the entire time. It was so hard. That proof was ridiculous. There's this Algebra 2 question that was so hard. Blah, 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 blah. You're going to freak out, and then you're going to go in the Chem Regents, and you're going to finish the multiple choice in 40 minutes, and you're going to be like, oh my God, okay, I can take my time. Take your time. You got a lot of it. Back to the polar stuff. So 2 different atoms usually means a polar bond. If they want you to evaluate what bond is the most polar, let's say you were comparing CH versus OH, you want to go to table S and you want to look at their electronegativities and you want to pick the one whose electronegativities differences are greatest. So if you were to compare hydrogen and carbon versus hydrogen and oxygen, you can see that oxygen has the higher electronegativity than carbon. So the oxygen-hydrogen bond is more polar than the carbon-hydrogen bond. All right, back to repeated questions. So this did pop up in 2013, just not quite the same way. Average kinetic energy is the same as temperature. So the one with the lowest average kinetic energy is going to have the lowest temperature. Don't let the other numbers confuse you. They do that not to trick you. They just really want to make sure that you understand the differences between the two units. Okay, I already see one I'm going to do in a minute, but let's look at these ones that come up a lot. Not that this comes up often, but just to make sure like you don't freak out. You don't have to memorize which substances are liquids at STP. Some of you might have memorized this because some of the periodic tables in your room are like color-coded, and bromine happens to be those ones that's like blue for some reason with the non-metals, because the answer to this question is bromine. Bromine is a liquid at STP. But if you didn't know that, you can go to table S, and what you can do is look up their melting points, and you can look up STP on table A, see that STP means 273 Kelvin, and whoever's melting point is above 273 Kelvin, but whoever's melting point, let me say that backwards. Let's start over. Whoever's melting point is below 273 Kelvin, but whose boiling point is above 273 Kelvin, is going to be the liquid. If the boiling point's above 273, that means it hasn't boiled yet, so it's not a gas. But if its melting point is below 273, that means it's already melted, so it's a liquid. Not that 19 is like a really popular question, but they like to ask questions using table S in some way, and it's usually those questions where you're like, how the heck am I supposed to know what a gas is at this temperature condition? You're not supposed to know, you're supposed to look it up. Trust us, 9 times out of 10, unless it's like a popular one like 19, your teacher's probably not going to know either. All right, 20 is an often repeated one, and I want to go over it because for some reason this year in particular, my students confuse them a lot. Equilibrium means equal rates, not equal concentrations. Concentrations are constant. Rates are equal. One year I saw them ask both of them. Like one was a multiple choice question where you had to say the concentrations were constant, and then there was a short answer question where you had to say the rates are equal. So there are some years where they throw both at you. Not usually. Usually it's one or the other. If they throw rates at you, at equilibrium, the rates are equal. If they throw concentration at you, at equilibrium, the concentrations are constant, which means not changing. Constant does not mean equal. It just means staying the same. 21's a barf question. Told you that pop up. Barf. Okay, I don't think this was the same exact question as June 2013 because I was tutoring someone today and we did this exact question with oxygen. But if it was the same exact question as June 2013, that would be hilarious. First, look at the reaction. Evaluate what's happening to the bond before you barf it. I'm seeing a bond here, and I'm seeing two separate things not bonded together. Clearly a bond was broken. No. Barf. Breaking bonds absorbs energy. Releasing energy forms a bond. So, apply it correctly. If this was in the reverse direction and two oxygens were forming O2, you would say energy is released. Releasing energy forms a bond. Earth. If you break a bond, then energy is absorbed. Breaking bonds absorbs energy. Bah. Put them together, Barf. I'm going to go over 22 because they throw in the word entropy, and I do say they like to ask about entropy, but there's a phrase to remember 22, so I figured this would be good to go over. Entropy and energy, lazy and crazy. So entropy deals with the term disorder. The more disordered you are, the crazier you are. Energy, if you're lazy, that's low energy. So high entropy, low energy, lazy and crazy. All right. Oh my goodness, I'm just going to do 27 right now. Told you they love to ask about electrolytes. And like I said, it's never going to be the same exact question. Like, that'd be nice if it was the same answer choices each year. It'd be a guaranteed, hopefully 100% of the state gets it right. But to solve an electrolyte question, you're looking for three things. You're looking for an acid, which is probably going to be on table K. You're looking for a base, which is probably going to be on table L. Or you're looking for an ionic compound, which means you're probably looking for a metal in a compound. Not just potassium. If it says K, K is a metal. K is not an electrolyte. But if it was KNO3, a metal in a compound, that's an electrolyte. So what you would do is you would go to tables K and L and see if one of these guys is on tables K and L first. Because quick glance, I don't see any metals. So it's probably going to be on tables K and L. I also noticed that a bunch of them had carbon in it. So table L is not going to have any carbon compounds in it. But table K does. And what table K has is CH3COOH and H2CO3. And I do think one of those was an answer choice. And it was CH3COOH. That's an electrolyte. The term to remember what the definition of an electrolyte is moving charged particles. The key word is moving. So they need to be in a liquid state or an aqueous state, with aqueous meaning dissolved in water. So before you just move forward, if they ask you why something can conduct as a liquid but not as a solid, you can say moving charged particles. If they ask you why this is an electrolyte, you can say because it has moving charged particles. They'd like to just give you some examples where they're like, why is this not conductive, but this is conductive? So the difference is, as a solid, NaCl is just like table salt. As a solid, it can't conduct because the particles are in that solid state. So they're relatively they're not stationary, but they're just kind of vibrating in place. They're not free to move anywhere. When you put it in water, those ions can split and you have moving charged particles. Potential energy of the products and the potential energy of the reactants. That difference, just want to highlight it, is not activation energy. That is the heat of the reaction. So when you look at those crazy diagrams like this, these potential energy diagrams, this area right here from the top of the hill and the reactants, this is the activation energy. I'm just going to put EA, the activation energy, versus the difference between the products here and the reactants here. This difference, that's known as your delta H, which is the heat of the reaction. Here we go. Which statement describes one acid-base theory? And we're dealing with those hydrogen/proton acceptors and donors. I told you it would pop up. It was on June 2013. Would you look at that? It's on June 2014. There's an acronym to remember that, and that's BAD. BAD. This one, I don't think I gave you guys throughout the year. I found it, and I was like, I like it. So, bases accept H+. That's the key, tricky part on this one. H+. And acids donate H+. So, be careful with 4. because it has H minus. So, bad. Acids are proton donors. Bases are proton acceptors. Bases accept. Acids donate. And some of these I'll probably go over tomorrow. So, like, when you see a question like 29, I really want to go over it now because I'm like, they might ask it. But I'm also going to do this tomorrow night. So let's, like Mr. G, don't do every question in this Regents right now. You're going to be here for 3 hours. 31, that's a silly question. So 31 is better. So in June 2013, they asked a question like 31, and 3 of the answer choices were just totally different elements. It was like H and K, Na and Ne. Which one of these are isotopes? And you're like, half of them aren't even the same element. Isotopes is, well, okay. I see where they're going at with this question. Let me read it. Which notation represents different isotopes of the element sodium? So they're like banking on you thinking sodium is S. Sodium's Na. Now, Regents Day shows up. You freak out. You're panicking. You forgot. Oh my God, I don't remember what K is. You can go to the reference table and you can look up the symbols of all the elements on table S. So table S is one of the, other than the periodic table, might be the reference table you use the most on Tuesday. It is a table of information. There is nothing to like figure out about it. It just tells you what this is for this element, including names and their symbols. So there's sodium. Oh, didn't highlight. There's sodium. It's Na. So when you see the word isotope, let's get rid of you. When you see the word isotope, isotope deals with masses. Isotopes mean same element, so it's same protons, different neutrons. Same protons, different neutrons. Charges, those are ions. When an element becomes charged, when an atom becomes charged, it turns into an ion. If you just change the mass, isotope. All right, back to the most popular ones. Gallium excited state. Told you they like excited versus ground state. We've already seen this exact question on the previous Regents, just with a different element. The first thing you got to do is find Ga on the periodic table and write down its ground state. So let's go to the reference table. Let's write down gallium's ground state. Gallium's ground state is 2,8,18,3. 2,8,18,3. One of the answers will always be the ground state, so you can just cross that out immediately. The key term here is excited state. That means you're going to take an electron from one of these lower energy levels and move it up an energy level. Meaning, don't take it away. Don't add one. Just take one that already exists and move it. So, for example, we know 4, answer choice 4 is wrong because it just added an electron to the last row. That makes it an ion. When you remove or add electrons completely, you get an ion. No. We don't want that. We just want to take one that already exists and move it to a higher shell. Answer choice 1 is wrong because it just took 1 out of 18 and then just tossed it aside like it was trash. Don't do that. Treat your electrons with respect. 2 is the right answer because it took 1 out of 18, made it 17, and shot it up here to change it from 3 to 4. Basically, you want to pick an answer choice where the amount of electrons stays the same. So in this case, we have what? 10, 28, 31 electrons, but you just move them around. So if the answer that you think is right doesn't have the same amount of electrons as what you started with, then you need to go back and try again. I'm not going to go over 35, but I just want to highlight that these big numbers in front, the coefficients, that means moles, not the little numbers. So just keep that in mind. When you're dealing with an equation, at least. If you're dealing with a formula, those little numbers do come into play, and like technically they mean moles. And I'm just saying if they're asking about the mole ratio in a reaction, look at the big numbers. Hey, 39. I told you they like to ask this question. Most polar bond. So again, this is table S, and then you're going to look at their electronegativity, and you want to see which ones are furthest apart from each other. So CO, NO, high, and Hickel. Co, no, high, Hickel. Co, no, high, Hickel. Co, no, high, Hickel. Okay. C and O. Co. 2.6 and 3.4, so that's a difference of 0.8. No. Okay, no is at a difference of 0.4. That can't be the right answer. High, so that's H is 2.2. Let's do Hickel first because I'm right there. H is 2.2 and chlorine is 3.2, so that's a difference of 1. All right, you're gone. And then I. All right, I's electronegativity is 2.7. 2.7 minus 2.2 is definitely not greater than 1. So it looks like Hickel is the winner. So the most electronegative, the biggest electronegative difference is the most polar. Aha, IMFs, here we go. Why they will ask this question most likely. What is the type of IMF, the type of intermolecular force seen in water that gives it such an unusually higher boiling point, even though when you bond hydrogen to everything else in oxygen's group, it's not even positive, let alone close to 100. Hydrogen bonding. If they ask for the type of strong intermolecular force, the type of strong intermolecular force, hydrogen bonding. If they ask which of these groups of compounds contain hydrogen bonding, remember that it's FON. You want HF, HO, or HN. Nothing else with hydrogen is considered the IMF hydrogen bonding. So hydrogen bonding is FON. Oh, would you look at that? A heating curve. Mr. G, how did you know that was going to appear? That's so crazy. It's like you're Nostradamus. Okay. Which line segment represents boiling? We might as well just go over the whole darn heating curve because they like these. So, first, we got solid, liquid, gas. Here, we have solid and liquid, which means we're melting. Here, we got liquid and gas, which means we're boiling. Every slope line, kinetic energy is going up. Potential energy is remaining constant. And every flat line, I kind of ran out of room. Flat line, potential energy is going up. And kinetic energy is remaining constant. The only difference between a heating and cooling curve is it's flipped. So you start at a gas at the top, then you're going to condense, then you're a liquid, then you're going to freeze, then you're a solid. Which means the kinetic energy for the slope lines, instead of it increasing, it's decreasing. And the potential energy for the flat lines, instead of it increasing, it's decreasing. Other than that, the principles are the same. So, I'm not even going to bother answering the question. I just literally went over like pretty much everything they can ask you about heating curves or cooling curves. You increase the temperature. What's going to happen when you're dealing with a gas? This deals with kind of ideal gas theory. The collisions are going to go up, 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 and the reactions are going to go faster, 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 faster. Hey, table M. Told ya. I'm Nostradamus, I'm telling you. I'm telling you. Thymol blue, pH of 11. Let's get its color. Okay, first things first. Person in my fourth block, or people in my fourth block, you know who this kid is. When you're looking at table M, all right, not going to name any names. But if you're watching, you know who you are. When you're looking at table M and the question's like, hey, what's the color of thymol blue? Maybe go to thymol blue. I'm just saying. Don't tell me what the color of litmus is. I don't want to hear you throw out the color red right now. Thymol blue has two options. Yellow or blue. Nothing else. So the pH was 11. Well, when it is 9.6 or higher, then it's going to be blue. So you're going to want to put blue, and you're not going to even want to put 1 or 3 because that's literally impossible for thymol blue. I shouldn't say that. Technically, red is. But according to your reference table, red is not, so don't put red. All right. I just don't want to lie to you. Okay, 44 through... I'll skip 45. 44, 46, and 47 are worth going over. They like these types of questions. 44, we're trying to get equilibrium to shift to the right. So I'm going to ignore all the answer choices, except catalyst is always wrong, so don't put catalyst. And let's just like predict. How can we get this reaction to shift to the right? So, rule number 1, if you increase the concentration of something, it will always shift away from that increase. So, increasing SO2 would shift it to the right. Increasing O2 would shift it to the right. If you decrease the concentration of something, it will always shift towards the decrease. Decrease SO3, shift to the right. Decrease the temperature, shift to the right. Last but not least, if everything involved in the reaction is a gas, if you increase the pressure, it will shift to where there is less gas. And obviously, decreasing the pressure would do the opposite. So in this case, since I have 2 plus 1, that's 3 moles of gases over here, and 2 moles of gases over here, an increase in pressure will shift to where there's less gas, which in this case is again the right. So the answers we're looking for are increase SO2, increase O2, decrease SO3, decrease temperature, or increase pressure. Adding more O2. Awesome. So again, generally speaking, you increase something, whether that be a substance or the temperature, it will shift away from that increase. If you decrease something, it will shift towards that decrease. If you increase pressure, it will shift to where there is less gas. And if you decrease pressure, it will shift to where there's more gas. Actually, I'm going to ignore this question, and we're going to say, how do we know if this compound is saturated or unsaturated? So, this compound is unsaturated because there is a carbon-carbon double bond. Unsaturated also means a carbon-carbon triple bond. (46) How do we figure out the oxidation number of an atom within a compound? First thing you want to do is kind of give them some space. Maybe give yourself some space, Mr. G, and do where you got room. Give them some space, and we got 4 O's, and say the charges or oxidation states of all of these need to add up to 0. So the first thing you should look up is an atom in this compound that only has one possible oxidation state, because that will make your life easier. So we got K, Mn, and O, not O4, just O. All right, K. K is always +1. Awesome. Okay, remember that. K is +1. Mn's a disaster. Oxygen is always -2. Okay, that's easy. I like that. So I know my K over here is +1. I know my oxygens over here is -2. Okay. But there's 4 oxygens. Okay. All right. So 4 times -2 is -8. There's only 1 potassium, so that's +1. What must the charge of manganese be so that all these numbers inside my box will add up to 0? Doing a little bit of mental math. 1 plus 7 is 8. 8 minus 8 is 0. I'm the best. +7. All right. Told you they like these pH questions. So, as hydronium goes down, that's a plus sign. pH goes up. As hydronium goes up, pH goes down. Okay, so for every power of 10 increase or decrease in hydronium, it's a one-step increase or decrease in pH. So if the pH moves up by 1 or down by 1, hydronium will move up and down by powers of 10. So I'm going to eliminate 1 and 3 because they say factors of 2. I want the answer to be factors of 10. If the pH is going up, which it is here, then the hydronium concentration should be going down. So I'm going to pick 2. Ooh, isomers. That did not pop up on June 2013. Might be a topic for tomorrow. Let's keep going. Like I said, they're going to ask you to draw the Lewis dot structure of something. Please remember that hydrogen is happy with a bond. No dots on hydrogen. If they ask for the Lewis dot structure, so in this CH3Br example, C's in the middle, we got our 3 H's, and then Br. You can't say you're finished yet. It didn't say draw the structural formula. It said draw the Lewis dot structure. So when you see dot structure, you have to keep in mind that every atom wants 8 valence electrons. This bond here already accounts for 2, so you have to make sure you give bromine 6 dots. If it said draw the structural formula, you don't need to worry about the dots. It's a little confusing, but if you want, when you draw structural formulas, if you want to throw in the dots, you're correct, so don't worry about it. Identify the type of bonding. Like I said, they like to throw out bonding questions. Potassium is K. And K, as we just noticed, is over here. Left of the staircase means you're a metal. If K is by itself, like there's no one else bonded to it, then the answer is simply metallic. If it asked you for, let's say, potassium oxide, then you would say ionic, because ionic needs a metal and a nonmetal. If it's just a metal, then it's just metallic. It's as easy as that. All right, like I said, I'm going to save some stuff for tomorrow. I'm seeing a few things pop up that I want to go over, but I also don't want to be on a live stream for 2 hours, so save some stuff for tomorrow. Empirical formula. I did say they like to ask about that. So glucose, they give you the formula up here and in the reaction. Empirical formula means simplified, so you need to reduce it as much as possible. 6, 12, and 6, I know I can just divide that by 6 and get C1H2O1. If you don't see it right away, start easy and divide it by 2. So if you divided it by 2, you get C3H6O3. And then hopefully it would be obvious that 6 is divisible by 3. So then you can divide them all by 3. I want to go over 58 just because they asked the exact same question on June 2013. Energy is on the right-hand side of the arrow. So that means it's exothermic. And an exothermic potential energy diagram starts high and ends low. So that's exothermic. Endothermic, aka energy going into or entering the reaction, would start low and end high. So exo. Oh my god, they threw in a table H question. That's crazy. Okay, 61. Compare the intermolecular forces at STP. They love it. They just like this question. So the question doesn't say what type exists. It just wants you to compare them, which is just asking you who has the stronger IMFs at STP. And the substance with the higher boiling point is going to have the stronger IMFs. So ethane's boiling point is -89. And it just straight up tells you that ethanol has a higher boiling point. So you would say ethanol is stronger. Ethanol has stronger IMFs. Like I said, I'm going over like the big repeated types of questions. 72 is a P1 V1 T1 question. So the tank had a pressure of 6.1 atmospheres at 293 Kelvin. If the tank is heated to 313 Kelvin, the pressure in the tank will change. Show a numerical setup for calculating the pressure of the gas in the tank at 313 Kelvin. So if they don't give you volume, you don't have to include it in your setup. If you want to like play it safe, just make it 1 or just leave it out. So the formula is P1 V1 over T1 equals P2 V2, I'm running out of room, over T2. And that's on the reference table. It's on table T, so you can always look up the equations. And the initial conditions were 6.1 atmospheres at 293 Kelvin. What is the new pressure at 313 Kelvin? So these were your initial conditions. It was like, what's the pressure at that condition? Not too bad. A few other things that they do like to ask about. I'm going to just move on for tonight. I'm doing the big repeated types of questions. Catalyst, they like to ask about. It lowers the activation energy. Too many of my students, when I put this on a test, just say a catalyst speeds up a reaction. Great. It tells you that. It was asking you to describe how it does that. So, like, answer the question. That'd be good. You can also say it provides an alternate reaction pathway. And that alternate pathway is one with lower activation energy. So if you go to those potential energy diagrams we just did, a catalyst would look like this. Start at the same spot and then just make the hill smaller. Because the top of the hill is the activation energy. Start at the same spot and make the hill smaller. Not the prettiest, but I'm drawing with my fingers and, I'm doing my best. Stop judging. Thank you. All right. What else we got? Sig figs, I'll go over tomorrow. MAVA equals MBVB. That is an equation on the reference table, so you don't need to memorize it. How do you know when to use it? Usually when you see a problem involving acids and bases, there's my acid up there, it mentions the word titration or it mentions the word neutralization. Titration is the easiest way because if you look at the reference table, it is literally called titration. So, that's nice. But if they don't say the word titration in the problem and it's asking you to determine the concentration of something or the volume of something and it says the word neutralization, then that's your other indicator that you should be using MAVA equals MBVB. So A and B literally stand for acid and base. M is the concentration, which is nice because the unit is just the big M. And V is volume. And in this case, we are trying to figure out what the concentration of the acid is. So our MA is unknown. Our VA was up here, 25. That's multiplied. Equals, there's our MB, because our base is KOH. Acids start with H's, bases end in OH's, times 18.5 would be the volume, and then you would not goof your algebra and divide both sides by 25 and get whatever that is. Answer ultimately unimportant. Would you look at that? Mr. G, you're like a genius. I told you they like to ask these types of questions. Entropy of the molecules in dry ice versus the molecules in the inflated balloon. So dry ice, that's going to be the solid state. In the balloon, that's going to be the gaseous state. And the balloon, so the gaseous state, is going to have higher entropy or more disorder, more chaos than the solid state. The solid would have a lower entropy. So gases are more disordered than solids. The particles move around a lot more. They take up the entire container, etc., etc. Don't say they're closer together as a solid. Say they are more ordered as a solid. So a solid would be more ordered. A gas would be more disorder. Okay, we'll do 84. We'll do all of these. State in terms of neutrons how an atom of tritium differs from an atom of hydrogen 1. So tritium here is hydrogen 3. It just wanted you to say neutrons in this case, so you're going to get lucky. But the difference is they would have the same amount of protons because they're both hydrogen, but hydrogen 3, hydrogen-3 is going to have more neutrons because it weighs more. The bigger the mass, the more neutrons it has. Determine the fraction of an original sample of tritium that remains unchanged after 24.62 years. So when you see a fraction question, you always start as a whole number 1. And you're going to keep just dividing by 2 until you get to whatever amount of time should have passed. So I'm just going to have this set up because after 24.62 years, what I need to do, since up here they didn't tell you what the half-life of hydrogen 3 is, that means it must be on the reference table. So I'm going to go to table N, and I'm going to look up the half-life of H3, and it's 12.31 years. So every 12.3 years, you're going to divide by 2. So every 12.3 years, you're going to divide by 2. So the question had you for what, 24 years? So 24 years is going to happen right here. So 12 plus 12 is 24. How much remains? 1/4. All right, 85, the last one of the night. We need to figure out the missing product for the decay of tritium-3. And it's not given on here. So we're going to have tritium-3. And I believe it's going to decay via beta, because it wouldn't be anything else. That wouldn't make sense. And we need to figure out what's missing. So this is when you divide it in half and say, I need to make sure these numbers are the same on both sides. So 1 here, -1 there. So this number must be 2 because 2 minus 1 is 1. That is 1, so they're the same. 3 here, 0 there. So this must be 3 because 3 plus 0 is 3, and they're the same. And then before you stop, make sure you look up who the atomic number 2 is. The atomic number 2, let's see, is going to be helium. So make sure you write HE in the blank. And that is part 1 of the most repeated types of Regents questions. I guarantee if you start looking through the 2015 through 2018 Regents questions, you're going to see similar questions. I already saw one right here. Barf. Let's see. Strong attraction for electrons. What is that? Metallic bonding. Let's see what else was the same in the 2015 Regents. Ideal gas. Different things are different. Oxidation states. Electrolytes. Hydrogen bonding. So like I said, they get repetitive. Excited state versus ground state. Stuff like that. So Tomorrow night, we're going to live stream again at 7. We have a review session in the school, in the TA, from 3 to 5. I'm in my room all day and probably will be bored, so I'm happy to have you guys stop by if you want to get extra help on anything, or if you just want a review. Aside from that, I'm going to just send you the link to my YouTube channel again so you can watch these videos at any time. You guys have a great night. Get some rest. Chemistry is on Tuesday, 8 a.m. Blue Gym, bring a pen, and a scientific, not graphing calculator. You guys are awesome. See ya.